But before that, we have a checklist. We have to ask these questions: what we are looking for, how to get the answer for it, what kind of system is this, is it open or is it closed, what equation that you want to use, what is ethane, what is saturated steam, what is the gauge pressure. Okay, so these are all the things that we need to figure out ourselves before we could really solve the problem. If we don't ask ourselves this question, we will not be able to solve the problem. And then what we have to do, we need to draw, okay, all parameters in the stream known to solve the material balance. Do we know everything or we didn't know some of it? So what are the unknowns? How do we calculate to know the unknowns? And is there any parameter that is not be able to be calculated because it is related to energy balance? Because we want to solve the material balance first. But if let's say there's something that we didn't know, then we have to calculate the energy balance and material balance together. Second step, determine the enthalpy for all stream. Which stream had specific enthalpy given? Which one that I had to find the info? What are my assumptions related to solving this energy balance? Okay, so what do we think about when we list down the equation of energy balance? What does it involve? What does it not involve? So what is the equation to be used finally? So these are the things that we have to ask ourselves. So let's look at the solutions, right? So when we have actually the heat exchanger, okay, what I'm trying to do is actually trying to label this in a simplified way, where you see that, okay, there is water, steam is coming from this side and steam is leaving to this side, okay, and then you know that there is no exchange of mass. Okay, there is no exchange of mass, but again, this is still an open system because there is something coming in and something going out, except that there is no exchange of water to this particular stream. It's just exchange of heat. So when you have the heat itself, okay, so when you have the ethane, so you need to know what will be the flow rate of ethane that is coming in and what will be the flow rate of ethane that is going out, okay. And this is where actually we start to calculate what will be the mass flow rate of ethane, because you were given at 795 meter cube per minute, so you want to convert this into kilogram per minute. Why is that you wanted to convert into kilogram per minute? Because the enthalpy that is being given, okay, it is everything is in terms of kilogram. So that's why you want to make sure that the unit is consistent. So you cannot just simply use for 795 meter cube per minute. You have to convert that accordingly to kilojoule per. You have to convert becoming the mass flow rate. So the mass flow rate, so meter cube divided by meter cube, and then you have minute per minute, 10 to the power of cube liter per meter cube is the same. And then you were given 2.5 bar gauge, and then you have the units, okay, which is R, and then you can have which is 1 over you have the temperature 289 Kelvin, which is given, okay, this is at 15 degrees Celsius, and you know the molecular mass and so on. So this is directly related to use of PV equals to nRT, okay, PV equals to nRT. So from here you just need to rearrange back this equation. So you make sure that M is equals to nRT over P. But you know V is actually what? Is actually the somehow it become considered as the density of it. But of course you can also calculate because you are given that 795, okay, meter cube per minute equals to N, which is actually M over molecular weight multiply with R multiply with T divided by pressure. So when you arrange back the equation, it's supposed to be 2.5 bar, okay, and then you convert into atmosphere because you are using the R, which is in term of the, sorry, you don't have to convert to atmosphere because R is given already in bar, okay. So you have 2.5 bar multiply with 795, right, and then you divide it by R, which is 0.08314, and then you divide it by 289 Kelvin, okay, and then you multiply with the molecular weight. So this is where actually you will get the mass, okay. So the mass flow rate will be given as 2.487 times 10 to the power of 3 kilogram per minute, and then you will given the specific enthalpy from here. So what you have to do is you just need to calculate the energy balance, and you know that the energy balance from the open system, there is no delta P, there is no potential energy, there is no kinetic energy, there is no work done on the system. So simply whatever is left is Q is equals to delta H. And you know that in order for us to calculate the delta H, we know already this amount, which is M. Okay, this is the mass flow rate. So mass is simply multiply with H out minus H in. Okay, so at H out is 1073, H in is 941. Then when you convert accordingly, you know that this is the amount of heat that is being provided from the steam, okay, to make sure that the ethane is heated from 16 degrees Celsius to 93 degrees Celsius. So that's the first answer. The second one is they were asking whether, okay, what's the question again? They're asking that whether the energy transferred from the steam goes to heat of ethane, at what rate in meter cube per second must steam be supplied. So we wanted to know, based on that particular amount of heat, right, how much steam that should be supplied. So we go back to the initial equation here. Q is equals to delta H, okay, because we also simplified like we have used this before. We know that the amount of heat that is provided here is the same as the amount of enthalpy, the change of enthalpy here. So we can use this particular equation, but now we relate it to steam, which is steam that is going out and that is coming in, right, and then the steam that is going out. And we know that the enthalpy change here, okay, the enthalpy is the Q here definitely will be negative value. Why does negative value? Because the heat is being transferred. So when heat is lost, then you put a negative term. Okay, then you put a negative term here. So assume that the heat loss to the surrounding are negligible, so that the heat given out by the condensing steam equals the heat transferred is equals directly here. You assume that there is no heat loss. Okay, so if you got from the table, so you go to table B6, then you go to 3 bar, okay, then you go to saturated vapor, they will get this is the specific enthalpy. And when you go to the liquid at 27 degrees Celsius, you go to table B5, you will get this is a specific enthalpy, right? So when you rearrange back this equation, then you'll be able to see that mass flow rate, this is something that you want to know, is actually the Q, which is you got from here, divided by the difference between HS1 and HS2. Okay, so when you put a division, because you know that why you put HS2 as 113.1, this is because this is the outlet from the heat exchanger, and then the outlet minus the inlet. So you see that when the outlet minus the inlet multiply with the negative 1, then you'll be able to get at 2.09 kilograms steam per second. And then you convert this into volumetric flow rate. So where do you get this value? Then you should check table B6. I want you to do it yourself. Try to check table B6. Where do you get this value? At which particular information that you get this value? Okay. And then what is being said here is that the flow rate is too low. Okay, the flow rate here is given too low. Extra flow would make up for the heat losses to the surrounding. Okay, 2.09 kg per second is a bit low in order for us to heat up the ethane from 16 to 93. In reality, we are actually supplying it more. Okay, because we know that there will be heat loss to the surrounding. Right, it is not properly adiabatic per se. Like there will be some heat loss, so you need to provide some more information. So in terms of the heat, what type of heat exchanger should be used? Usually in this particular system, when you learn the process heat transfer later, it is of counter current flow. What does it mean by counter current flow? Is that right now, if you can see now, this is an arrangement of co-current flow. So if it counter current flow is a way that this particular stream is somewhere around here and the arrow is going in this direction, and this one will be at here or the other way around to the top. Okay, so that is counter current flow. Because if let's say you have for example, like you have two flow coming together. Okay, if let's say this is steam and this is ethane, okay, in the same direction. So initially the temperature of the steam is very high, okay, and then it will actually drop very low. Okay, so this is the temperature profile lah. The temperature is very high and then suddenly it goes very low, and the temperature of ethane will go up, right? But after some point, because the temperature of the water, the steam is dropping, so maybe it would not reach 93 degrees Celsius and it will started to fall, and you may not be able to get 93 degrees Celsius. So that is why actually when you start to have heat exchanger which is in counter current flow, so when you have the steam is coming in at very high temperature and suddenly it goes down up to 27 degrees Celsius, here in ethane, because it's coming from this direction, okay, this is, so the temperature will develop in a way that initially is very slow and then it's gonna goes up, because at this particular point it meets with a very high temperature of steam, so you will get at 93 degrees Celsius. This is as expected. Okay, so that's all that I'm going to share for this lecture. Hopefully that you watch it, try to understand it, read the textbook if you want to know more. Okay, so see you in the next video. Assalamualaikum warahmatullahi wabarakatuh. Bye.